Okay, Michael, are you ready to begin?
Yeah, I'm ready.
Okay, well, welcome to the Winter EM course here at SEMC. Today we have Michael Alink, who leads our hardware team here at SEMC, also the engineering team that has been really able to keep our microscopes with high uptime, and that's very important for a facility. So Michael, please take it away.
Okay, good afternoon. I'm Michael Alink. I'm a research engineer at the New York Structural Biology Center. I want to talk about new cryo EM hardware we have on site. And I also want to dive a little bit into the existing hardware we have, so we get like a little bit perspective of where we are going. So the latest microscope we have is a Cryo 7, a fourth generation Cryo STEM. The design is for high throughput. It has Fringe-free imaging. That's something I will go into a little bit later. It has aberration-free image shift, Falcon 4 camera, and it has a new data storage format. It's an electron event representation. So before I go into that, this is one of our older scopes. It's a TechNI. Basically, a TechNI and a Cryo still have a lot in common. Both microscopes have a source where the beam is originating. It has the condenser system, so that's basically your beam forming part of the microscope. It has an objective area, it has the magnification area, and then it has a camera area where the images are recorded. Basically, what you see here in yellow is your beam, and everything in green is the image. When you go through different mags of the microscope, your beam not necessarily needs to change. So your condenser system does need to change. Even if you were to press the diffraction button on your scope, you still have the same beam. The projection system is everything that does the switching between normal mode and diffraction mode and the magnification range. So it's very good to keep those things separated. We also have a Hitachi. It has the same build-up. It has a source, it has a condenser system, an objective system, and an image forming projection system. And just like a Joule, it's not a Hitachi. The Titans we have on site is definitely not a TechNI. The optics is quite different. So one of the main differences that Titan has is the constant power. So basically the power that goes in all the lenses, be it the condenser system, the objective system, or the projection system, it's always the same power. So there's two coils, one goes clockwise, one goes anti-clockwise. And by just diverting different power to different coils, you maintain the same wattage that goes into the microscope. So you get the same load on your heat, but you change the magnetic field, so the strength of the lens. And that also makes that the alignments of these systems is a little bit more complex on a Titan than on the TechNIs. They're split into column alignments where you can tune every lens separately, and there's the direct alignments. That's actually the main alignments that's being done by the user. So normally column alignments are so stable you don't need to touch them. So what you do not need to do is realign your microscope daily, especially not on a Titan system. These systems are so stable that normally the column alignments needs to be touched up like once a year or so, and we have a staff to do that. If you don't know exactly how to do the alignments, then don't even go in there, because there's a lot of it's the master of destruction. So there's a lot you can do there. And again, the user is often more unstable than the microscope or the room. At structural biology, we monitor the rooms. You can see that in this graph in the lower right. You can see that actually this is Cryos 5. We have 7 cryos in total. You see that the room stays almost within 1 degree, which is well within spec. So it's the microscope and the room is really stable. So how you set up your scope, just to go quickly through it. First, you want to be at eucentric height, and keep in mind the height is just a mechanical height. So it's the mechanics of the stage that brings the stage, the sample to a certain mechanical height. Then you want to be at a eucentric focus. A focus is an electric height. So it's the electric current going through your objective lens. On a Titan, the objective will be excited about 80% at eccentric focus. On a Tecna, it might be 90%. You want to have a parallel beam. The objective needs to be stick-mated. You also check the condenser and the projection, but the objective is the main image forming part. So you want to have that stick-mated as best as possible. You want to be coma-free, and you want to check your dose rate. So if you do all of that perfectly and everything is set up correctly, your microscope is stable, and especially the room is stable. So the sample it's not drifting. You will see something like this. So you see nice round rings, and the red line you see here is this is something called tone rings. This is something that engineers use to check the optical transmission of the microscope. So the signal on the left, the image, it has like a little harmonic on it, a little frequency, and that frequency is superposed on the signal that comes through the whole lens system, and you should see that as wiggles going through here through the system, and you should be able to extend this all the way to 3 angstrom. That's what the Titan should show you, and as you can see, one of these systems even makes it to 2.3 angstroms. How do we get to this? The first thing to get is a very stable source. You need a stable gun with a good brightness and low energy spread. That means the temperature has to be at the right set. It should be around 1800 Kelvin. So that's what research has shown. If the temperature is too low or the extraction voltage too high, so you can imagine if the extraction voltage goes up, the hottest electrons are pulled out the most, so the temperature goes down. Then the tip, it will evolve in the single facet. If it's at the right temperature, the end form is stable and will result in a stable current. If the temperature is too high, or if the extraction voltage is too low, so too many hot electrons stay in the tip, then the end form will evolve into a blunt round shape. That's pictured here on the left, and you get very low brightness. So it's pretty important to have your gun set up correctly to get a high brightness and a low energy spread. So the extraction voltage, it increases the energy spread of the electrons. Too low of a temperature makes the emission sensitive for pressure variations. So the compromise is to have the temperature around 1800. You do this by checking the screen current. And a good rule of thumb is if you were to go to spot size 1, gun lens 1, the screen current should be about 50 nanoamps. And at this setting, you have an acceptable energy spread, you have a good brightness, and you have a reasonable stability. So here's a little question to test your own experience. Test if you know what happens when you would change the high tension, if you would change the extractor voltage, and if you change the gun lens settings. So basically, what happens is this crossover that's formed in the gun, it moves. And if you make a stronger gun lens, you basically pull the crossover into the gun. If you make a higher extraction voltage or you lower the high tension, basically the crossover goes down, and at some point it will be out of the gun electronics. And once the crossover is outside the gun lens, then it's very hard to focus it stably and to get a good beam through the column. So if you have no feeling for this, you might want to back up the alignments and try it before your session. But if you've really no experience with gun alignments, it's best to leave them alone, because there's a lot of variables that affect the performance of the whole microscope. Gun alignments, they're really stable on a Titan. On a Tecna, you might want to check them every then and when. Basically, you want to have a stable spot. I've put 2 images here. One shows a bad gun alignment, one shows a good gun alignment. You see here that the spot is nice and round, and it has the bright spot in the middle. You only align it when needed, and the tip is to do the whole gun alignment, so not just one step in direct alignments. And it's because the gun crossover is the most important step, and it's only in the whole alignment session where you can do the crossover correction. So therefore, only do a complete gun alignment and avoid direct gun alignments. Once you're done, save the gun alignment in the FAC registers. That's what they are there for. Normally, I have to say, we don't change the gun settings too much, but nowadays we do some research with microED, and that's done on a very, very low dose. So you go to a higher gun length, and that means that the user, you should offer them 2 good gun alignments, and that's why we change them, and it has to stabilize. So you might sometimes have to do some gun checkups, especially on the glaciers. Then we get the condenser system. So if the last condenser crossover is at the front focal plane of the objective lens, so here on the bottom, this is your objective lens, and this is the last condenser crossover. If it's at a front focal plane, then the diffraction pattern is focused at the back focal plane by definition, and we have parallel illumination in the objective lens. For the rest, everything is fixed, and only the C2 aperture determines your illuminated area. So if the last condenser crossover is at the front focal plane, then the diffraction pattern is focused at the back focal plane. So again, I have some questions here just to test your background knowledge. So how do you find parallel illumination? Where's the back focal plane? How can you put your eyesight at the back focal plane? How do you know you're focused at the back focal plane? What is also in the back focal plane? How to focus the back focal plane? How to find the front focal plane? And when am I parallel? That's probably the most important question. So the back focal plane is where your diffraction pattern lies. How do you can put your eyesight there? Just switch to diffraction. How do you know your focus? So you want to find something fixed in the back focal plane, and that's most often is used the objective aperture. How can you focus there? You sharpen the objective aperture. How to find the front focal plane? So what you do is you change the intensity till your diffraction pattern is in focus. So when are you parallel? So when simultaneous, the diffraction pattern and the objective aperture are focused, then by definition, you're parallel. So here's an example. You see the diffraction pattern, that's these rings, they are nice in focus. And this little cutoff here is the objective aperture. And if you check here, you will see that also the objective aperture is sharp, it's not blurry. So in this case, it's a nice check. So you have your cross grading in, you switch to diffraction, and then you can see that you're actually parallel. And the rules of parallel illumination, parallel settings should not change when you only change the spot size. If you change the mag, keep in mind the magnification is only determined by your projection system, and it shouldn't change if you change your C2 aperture. If you're while being parallel beam size, you can only change it when you change the C2 aperture. It should be consistent. So if you go from a 50 to 100 micron C2 aperture, the beam should be twice as large. So that's a nice check you can do. And also the beam sizes should be constant for each C2 aperture when you change the spot size, and definitely when you change magnification. Here's some images. This is basically on a glacier. So this is a Techni column. This is microprobe. You can see how small the beam is, but you will still illuminate on a R22 quantifier. You will illuminate multiple holes. So in this case, you would be able to image every other hole. If you go in nanoprobe, so that's why we use nanoprobe a lot, then you see the beam is much smaller, and you could be able to image every hole. So that's why we use a nanoprobe. This is Titan. Titan has a 3 condenser system. So it has 3 condenser lenses, and 2 lenses are used to change the intensity of the beam, and 2 lenses are used to change the size of the beam. Within that range, so you can imagine with 3 lenses, you have much more range. The beam is always parallel. So by changing 3 lenses, the idea is that the crossover, so you see this blue line here, the crossover is always at the same height above your objective lens. So the imaging is parallel through your objective lens. So that makes the Titan system so such a huge range for imaging. So a Titan the same. whenever in a parallel range on a Titan, if you go to eccentric focus, if you insert your objective aperture and you go to diffraction, your diffraction pattern should be sharp. So it must be like in this right image or very close. So you have a sharp diffraction pattern and you have a very sharp objective aperture. If that's not the case, then something is definitely wrong with the alignments or with the hardware. And most especially, it did not leave the factory like that. So that's it's not parallel. It's the first check, and then yeah, it has to be addressed. This is nanoprobe on the cryos. You see that there's no compromise with cryos on dose rates. There's no wasted area. You're perfectly parallel, and there's less strain on grid quality. So one good grid square is enough. You can see that you can do multiple exposures in one hole. And I have to say, at Structural, we did a lot of testing. If you set up your experiment correctly, you can start it at the middle, and then by just moving the beam, it shouldn't give any additional aberrations. And you can even set it up that with one stage move, you can image multiple holes. So that's very stable to do with a cryos. Here's a few tips and tricks to speed up data collection and to set up your experiment. When you load a sample, the first thing you want to do is press eccentric focus, so you know your objective lens at a nominal strength. Then you want to set your sample at eccentric height. So you could do it with the alpha wobbler. There's also the quick method. So what you do is you move the Z a little bit, and you get a caustic ring. This is ring around the center beam. If you turn the focus, it would have the same effect, but you get the caustic ring. And then you want to find the position of your sample height, where it's exactly at the height of your crossover. So your image looks like this. So there's like no caustic ring anymore. It's a very fast way to find your eccentric height. Stigmation, there's also a trick there. So once you're at eccentric height and you're at eccentric focus, you want to lower the Z a little bit, so you see your caustic ring again. And what you do is with your objective stigmator, you adjust the caustic ring to be round. So stigmator value should typically not be larger than about 0.1, not more than 10%. Otherwise, most probably the eccentric height is off. And this is a quick way to find the stigmation. Nowadays, there's a lot of software packages that do this automatic for you, but it's good to do it already roughly in the good ballpark. Once you're at eccentric high and eccentric focus, you lower your Z a bit, and then again you see your caustic ring. What you do is you activate the rotation center. That's in the direct alignments. You can stop the wobbling. It's going to wobble your objective lens, but you stop it by using the coarse focus button. So that's the outer ring on the focus knob. And what you want to do is bring the central spot in the middle of the caustic ring using the multifunction buttons. Keep in mind, coma-free alignment and rotation center use the same button, so you cannot optimize both. And then the last thing is the pivot points. Be aware, pivot points are focus dependent. As for single particle, you change the focus, the pivot points will change. It's unavoidable. Therefore, never correct the pivot points at a specific focus other than eccentric focus. Because pivot points are focus dependent, the beam will move while imaging at different defocus setting. So it's not beam instability, it's the fact of life. Your parallel beam size should therefore be chosen a bit larger than the size of the diagonal of the camera surface. Otherwise, yeah, you lose parts if you tilt the beam a bit. Here's a slide I put in about resolution. So cameras. This is to explain the Nyquist frequency. So 2 pixels on the camera is the smallest distance you can resolve. This is called our Nyquist frequency. Otherwise, 2 envelopes will overlap. So full Nyquist is 1, it's normalized, and it's the highest resolution you can get at a certain meg. So let's say you're at 75,000 meg, your pixel size is 1 angstrom. So Nyquist is 2 times, is 2 angstrom. And if you only attain a half a Nyquist, then your resolution will be 4 angstrom. And yeah, and so you can do the math. So it just adds up. So to recap all this information, how to set up your scope. Normally, once you're a little bit proficient with a cryos, it should not take more than 15 minutes. So what you want to do is determine your desired resolution. You check the sensitivity of the camera and you determine the pixel size. The pixel size determines the mag. For example, 1 angstrom on the Titan is about 60 kx. And you set this mag. You insert the cross grading. You go to eccentric focus. On the Titan, the objective lens should be close to 80% excitation. On the Techni, even 90%. You go to eccentric height using your alpha wobbler or your caustic image, and then focus the spot. Then you lower the Z height, you do the rotation center and the astigmatism, and then you bring the Z height back to a spot. Last step, pivot points, go to diffraction, insert objective aperture, and then you can see if your beam is parallel illumination. So then on the Titan, simply set the beam size a little bit larger than a camera diameter, press diffraction and insert the objective aperture. Both should be focused. So this brings you at eccentric height, eccentric focus, parallel illuminating. It's roughly stigmated and you're roughly coma free. And then if everything is set up correctly, you should see something like this. Then, so now it comes to an interesting point. On our Cryo 7, the generation 4 cryos, we have something called fringe-free imaging. And basically, normally you would see on your image, you would see Fresnel fringes. And those are basically images of diffraction of your C2 aperture. So you can imagine if an incoming wave hits the C2 aperture, it gets diffracted around the edges, and you will see them out of focus on your image. Now, what does fringe-free imaging do? The upper pole piece of the objective lens produces an image of the C2 aperture, and the image does not always coincide with the sample plane. Simultaneous imaging of the focus sample and the out of focus C2 aperture by the lower pole piece gives you these rings. So when the C2 aperture is imaged out of focus, wave interference at the edge of the condenser beam appears as Fresnel fringes. Now, what's the trick? So here's a little bit more background on diffraction. You might want to read up on this. It's more theory. So the trick is to move the stage up and move it so far up that the image of your C2 aperture coincides with the image of your sample. So the Fresnel fringes reduce, are no longer reducing the useful beam area, and they won't limit the number of images that can be recorded. To minimize those fringes, we're going to adjust the stage position up about 50 micron to the image plane of the C2 aperture. And then the lower objective pole piece strength is adjusted so that the sample is focused on the camera image plane. And then both the C2 aperture and the sample will be in focus. And no or very few Fresnel fringes will be visible in the image. In theory, fringe-free imaging can be achieved on any microscope by driving the stage motor up to change the sample height to C2 focus and adjusting the defocus of the sample. However, this means the sample will no longer be at eccentric height. A thermal fissure has a modification, the fringe-free imaging. It's a mechanical stage adjustment where the whole stage is lowered to the required C height using stage wedges. And if the stage goes down, the sample goes up. So keep that in mind. And the pivot point is where the wedges hold the stage. So when you adjust the stage axis, the tilt axis and the eccentric height need to be retuned to work optimally at that stage location, and then allow seamless acquisition of single particle and tomography data with fringe-free imaging. It's compatible with all cryoses. So we have generation 3 and 4 systems. So we are currently discussing if we want to upgrade our generation 3 cryo systems. On generation 1 cryos, fringe-free imaging is only compatible with Plan 3 autoloader system. I'm not sure if there's still generation 1 cryos in the field. We don't have them yet, structural biology. The fringe-free imaging modification is not provided for glaciers in Arctica, and it can only be used in nanoprobe, so there's some limits there. This is a little bit the close-up of the stage hardware. What you see is the side of the stage. The holder is entered from the right, and then the wedges are below and above the stage. And basically, you move the whole stage up and down. The procedure is you go to nanoprobe parallel illumination. You go about 96,000 meg in TEM, or an FTEM 165,000 meg. The beam diameter is about 600 nanometers. The objective length excitation will be increased until the Fresnel fringes are no longer visible. And then the image is focused by lowering the stage Z height, and the stage wedges are adjusted to redefine the U-centric height. So that's a procedure that needs to be done. It will take a couple of days. So in case you want to upgrade systems in the field, please consider some downtime there. Also, the beam, the form of the beam will change. It's normally in TEM, it's like a nice round beam with hotspot in the middle. With fringe-free imaging, it will look like the one on the right. So you will never get it the beam perfectly stigmated. And then condenser astigmatism is best optimized by adjusting the stigmators to create a round beam in parallel mode, instead of optimizing the spot shape by condensing the beam. So your beam looks a little bit weird, but you get used to it. The magnification range, fringe-free alignments are done at medium-high SA, so about 96,000. The beam diameter is about 600 nanometers. When the beam diameter is varied by adjusting the condensed lens, it also affects your focus of the C2 aperture, and it affects the quality of your fringe-free imaging. The beam diameter changes are needed when working at different mags. So if you go a little bit different mags, so higher or lower than 96,000, it will affect your fringe-free images. The claim is it will not limit the use of fringe-free imaging for mags that are typically utilized for single particle experiments with a narrow beam diameter. A similar effect will occur when applying an additional defocus with the objective lens. Such a defocus will change the focus of the C2 aperture and introduce some fringes around the edge of the beam. On systems with a fringe-free imaging configuration, the recommended way to adjust the beam tilt pivot points for TEM is to work with a parallel beam and change the mag to allow displaying the full beam on the FluCam. Pivot points are then adjusted by minimizing the beam movement during the alignment. Here's a few bonus slides I found. Next to the fringe-free imaging, there is also a single tilt holder available for the Cryo Generation 3 systems. So that's something I'm trying to detail here. You might be familiar with the Cryo Generation 3 holders. So they have alpha tilt. So the holder comes in from the bottom and the autoloader comes in from the top. And these two fingers, the blue and the yellow, they hold the cartridges once it's loaded to the stage. Now, the design is such that you can move these fingers and therefore rotating the sample in plane. Yeah, keep in mind that the whole mechanics is quite elaborate to make this work. So there's an upgrade available. It turns out that for a lot of workflows, you don't really need this in-plane rotation. So you could do a single tilt holder, which is only tomography, the alpha tilt, and then it's much more stable. Temperature is also stable, and it's very, very good for tomography. So that's an upgrade that's available. It requires splitting of the column because the braids that cool the holder, they are touched by screws to make the resistance for the heat path as low as possible. So the engineer has to open the column, loosen the screws, put a new holder in, and then align everything with the autoloader again. Another detail what you can see here is here's the objective aperture. So you can imagine the room budget below this cryo box is quite tight, so everything has to be checked. And another thing that's interesting is this is the temperature sensor. So not to affect the quality of your imaging, the temperature sensor had to be moved a little bit away from the holder. So when you see sample temperature in the UI, you're actually measuring a little bit away from the beam. So it's also interesting to know. It's a little bit perspective. Again, here you see your temperature sensor. Here you see the holder, and here you see the braids that make sure the sample is cooled to liquid nitrogen temperatures or close to them. The braids will not change when you put a new type of holder in. So it's the aim is to get a low sample temperature, no influence on optical performance, improved tolerances, mechanical robustness, and better tomography specs. It's also easier to service, and the price goes down a bit. So why do we want low temperature? This is probably familiar. This is more a picture of that's published a lot, but so you have different kinds of contaminations. And we have like black spots. We have ice growth. We also have this leopard skin that's in between the protein, and basically it's a surface contamination, and it seems to be related to mobility of the surface layer. And if the temperature is sufficiently low, then this mobility is sufficiently low to allow good imaging for a couple of days. The temperature goes up, then this leopard skin is building up way too fast. So that's why it's so important to have that design optimized. Oh yeah, this is something I found interesting. We talked about the parallel beam. So here you see actually the pole pieces, the upper and the lower. So between these pole pieces is where the sample is loaded and where the beam is parallel. Here's a little calculation that shows with both the existing holder and new holder that both the temperatures that have been measured and calculated by just measuring the influx of heat from the beam, it still keeps the sample cold enough to prevent leopard skin from happening. Here's another thing I wanted to show. A lot of questions I get on this institute about tanks that freeze up. Especially there's a 22 psi blow-off valve on our liquid nitrogen tanks, and sometimes it happens to freeze and it freezes open just due to excessive ice build. What you see is normally during an autofill, you will see that it fills your dewars and then it stays stable, it fills up. So at Structural, we have a scale that measures every tank and it monitors actively via an active Ethernet network what the weight of the tanks is. And if one of the valves freezes, you will see like a 45-degree slope, and it signals that the tank is has a frozen valve, and you don't have enough cooling temperature to fill pressure to fill up the dewars, and then the sample might inadvertently heat up. So it's a little thing we have at the institute. There's another thing we monitor. This has to do with the RGA. So RGA is like a mass spec. So normally you use it for leak testing around mass 4 helium. We use it for mass 18, and it tells us when we warm up the system. So basically you want to expel water from the column and pump it away with the turbo. And we look how high peak 18 is. So peak 18 in the system, and we see if it's still useful to cryocycle, or if the water background is already below like the helium or the hydrogen peak. If it's below a certain threshold, you just know that, especially on all the systems, that the column is so dry that it doesn't really make sense to prolong your cryocycle. So, here's the last thing I wanted to show. This is something that Thermo Fisher offers on their Cryos 4, the Falcon 4. This is EER, electron event representation. It's a data format. Basically, a normal conventional representation of Cryo EM movies store pixel intensities for each exposure. With EER, you store a tuple of position and time, and it indicates where and when electron was detected on the sensor. It's rather new. It's like an it saves a lot of data, so the images are much smaller, and it's available on Falcon 4. So it might be interesting to experiment with that. If you want to use it at the moment, you could do it with Reliant. There's a separate branch for Reliant. Reliant EER is available to work with this. So it's something I wanted to mention. Okay, that's it from my side.
Okay, so I'll kick off the discussion. So if you have a lot of questions, then you can put it either in the chat or message us directly. But I think something for a point of clarification, we have the microscope, but then we have everything supporting the microscope, and that includes water, compressed air, liquid nitrogen, and then there could also be environmental conditioning like a table to remove vibration or EMI cancellation. So of all of the external factors to feed the microscope, I guess maybe I also emitted electricity, including a UPS, external factors between environment and what needs to keep the microscope running. What do you feel is a failure point that hurts a facility the most?
One thing that's very important is the environment. So if the temperature varies by 4 or 5 degrees, then forget it. Your sample turns into a Ferrari, and it's very hard to follow your area of interest. I know that nowadays the camera with the movie modes, they're forgiving, but the facility just has to be stable. So you don't want any sound influences, no magnetic field, and most especially temperature has to be stable. So that's like the basic to start with. And from that point of view, starting point, yeah, if you have a good design microscope, yeah, then I think you have a fairly good setup.
I think something that users are very concerned about is contamination and keeping their samples in frozen hydrated states. So you were going over the cryo box and how different microscopes keep not only the sample cool, but reduce contamination. Could you comment on the different KV microscopes and the solutions that they use, and compare and contrast why you would go with one design versus another?
Yeah, there's so basically all the type of microscopes, they go like 120 kilovolt or 200. The vacuum systems are also not so good there. So the mean free path is worse. Typically, those kind of microscopes have side entry holders, which allow a lot of contamination to go into the system. And also, the resolution was a little bit lower, so it was less demanding. The newest system with autoloaders, they have a fixed holder. The octagon chamber is completely sealed, and then you can have very stringent demands on your cryo service. So if you have the Titan, it has this cryo box that shields your sample, so it takes away the moisture. It has a dedicated chimney, so the water molecules has to be exactly vertical to make it through the chimney, else they will just get trapped on the cold wall. And then also the design of the duo is such that the resistance for the heat to go into the duo is as small as possible. So then for these really high-end systems around 300 kilovolt, yeah, you have really good low contamination rates.
Michael, could you comment on how modular a microscope is, that you can add, a GIF, you can add a different camera, or you can even change electron source. So could you elaborate on, is it better to have something integrated, or is it more convenient that a consumer can a la carte add things, maybe pros and cons?
Yeah, I prefer the concept of modularity. You see it in multiple businesses. The Hubble telescope was also very modular, which allowed it to be serviced very easily. Although with a Hubble telescope, you have to have a space shuttle and load the thing in. But with a cryos, you can do the same. So you have all these modules. You have the gun area, you have the condenser, you have the objective and the projection. You can split the column at every junction. And sometimes, so a lot of issues are solved quite fast. So there's a lot of common issues, but they're solved fast. But there's a few difficult issues that take a long time, that take like 3 or 4 weeks. So that's also what you don't want at the customer side. The good thing is that the Titan has been designed, if ultimately it's too difficult or too time consuming to fix like a gun that's unstable or a lens that's unstable. You can just take the whole lens section out and put a new one in. So for service perspective, that's a big pro. In the future, if you want to upgrade your system, so if you want to have, so we did a whole bunch of upgrades at New York Structural Biology. We upgraded cameras, we upgraded GIFs on system that didn't have a GIF. We've changed holders from dual axis to single axis holders. We changed guns, and they give us a large versatility of what we can offer to our users. And I know that in the coming 2 months, we get a new type of gun, a cold vac, and we get a new kind of energy filter that's actually now offered by Thermo Fisher and not from the known GIF from Gatan. And all those units can go seamlessly on the column without any issues.
So if no one else has other questions, I'll keep on asking. So a couple more questions. In terms of lifetime of an instrument, how long would a base microscope be useful for its use case? And then how much can be extended with software upgrades and or camera upgrades?
Yeah, I have to dive a little bit in my memory here, but I know there is still a few CMs in the world that are in use. Those are very early electron microscope that were computer controlled. Then the TechNI platform came. TechNI has proven very, very stable, and even at our institute, we still have a TF20 that users just love because they're so familiar with it. And as long as the stage is the mechanics is a little bit starting to give way, so it has O-rings, feet on O-rings that dry out. I know that the gun is no longer the latest, so at some point. Yeah, I think the mechanics after 20 or 30 years, at some point you get like at a point where it's just too expensive or too cumbersome to maintain. But I think from a technological point, you can, well, the camera can be upgraded and the source. So it's I think 20, 30 years is definitely a very a useful time span.
So then on my last question will be on the service perspective, how long would you want to service a microscope? Would you want 20, 30-year microscope to be servicing and to keep in production?
Yeah, I should talk to our thermo service engineers. I know they're now so familiar with the TechNI because it has been around for a long time. It takes more and more time because on these older systems, once you start taking things apart, then especially yeah, O-rings, they rip, but there's different springs. Everything is brittle, so a lot of stuff breaks while you're servicing it. And also the younger generation, they get trained on much newer systems. So at some point, the knowledge is also depleting. And you also part availability is at some point a problem. So I know Thermo does when there's like a chipset or a certain mechanical part, if it's no longer available, they do a last time buy. But at some point, there's just no parts that are available anymore. So at some point, it becomes too cumbersome to keep it in operation.
Okay, last call for questions. Otherwise, this Wednesday, we'll have our first journal club. And hopefully that'll be exciting. We'll be talking about vitrification methods, one of the original Jacques Dubuchet papers, and a paper that's a little bit more modern on blot-free vitrification. Okay, I don't see any more questions in my chat. So let's thank Michael for a wonderful lecture. And as soon as he gets off, I'm sure he'll give me a PDF version of his slides so I can post it on the website.
Oh yeah, thank you.
Okay, thank you so much.